if we have mastered the hyperbolic functions? Well, at any rate, here's another interesting question that comes up, and I thought that we should mention this also. Notice that we arrived at this result by doing the thing in reverse. You'll recall that we started with y equals inverse hyperbolic sine x and showed that the derivative of that function was 1 over the square root of 1 plus x squared. An interesting question might have been, what if we had started with the integral being given and we hadn't have differentiated the inverse hyperbolic sine? How could we have got from here to the inverse hyperbolic sine? And I thought I would mention this because there may be some confusion, especially if you've taken to heart certain advice that I gave you earlier when we dealt with the inverse circular functions. Remember, I told you that whenever you see something like the sum of two squares, to think of a right triangle. In other words, if you have the square root of 1 plus x squared, it seems to me that the triangle that suggests itself is something like this. In other words, if I call this side x, I call this side 1, and this the square root of 1 plus x squared, it would seem to me that I could make a circular trigonometric substitution over here. In fact, what seems to dictate itself over here is to make the substitution let tan theta equal x. Now, if I let tan theta equal x, watch what happens here. I get secant squared theta d theta equals dx, taking the differential of both sides. I also get, looking at my reference triangle, that the square root of 1 plus x squared is secant theta. See, this over this is secant theta. At any rate, then, making this substitution in here, replacing dx by secant squared theta d theta, and the square root of 1 plus x squared by secant theta, I wind up with integral secant theta d theta. Now, you see what I've done here is I have successfully transformed an integral in terms of x into one in terms of theta. But without belaboring this point, it turns out that at this stage of the game, we do not know how to exhibit a function whose derivative with respect to theta is secant theta. In other words, we've made the substitution, but we wind up with an integral that's just as tough to handle as the one that we started with. You see, in this case, trying to make a circular trigonometric substitution wouldn't have helped us very much. What I'd like to show you is, again, an interesting connection between the circular functions and the hyperbolic functions. Namely, when we did this particular thing over here using our reference triangle, what was the reference triangle really taking the place of? Notice that if we let x equal tan theta, certainly 1 plus x squared is 1 plus tan squared theta, but there is a trigonometric identity that says 1 plus tan squared theta is secant squared theta. I think the usual way that it's given is that secant squared theta minus tan squared theta is 1. This is the result that we used. We didn't really use the triangle other than to get this result more visually. The point is there a hyperbolic function that has the same format? Is there a hyperbolic identity which says that the difference of two squares is 1? The answer is, well, remember, our basic hyperbolic identity is that cos squared theta minus sinh squared theta is 1. In other words, structurally, notice that sinh theta does for the hyperbolic functions what tan theta does for the circular functions. See the common structure here? We're going to reinforce this in the next block by doing problems like this again. But for the time being, I thought I would like to point this thing out to you. In other words, what the approach is that when you try a circular function substitution, and it doesn't give you the answer that you want, meaning that you wind up with an integral that's just as tough to handle as the original one, you look for the corresponding hyperbolic function. In other words, what hyperbolic function plays to the hyperbolic identity the same role that this trigonometric function played to the circular identity. In other words, in this case, we replace tan theta by sinh theta. In other words, instead of making the substitution x equals tangent theta, we make the substitution x equals sinh theta. And now watch what happens as we work this thing quite mechanically. The differential of sinh theta is cos theta d theta, and the square root of 1 plus x squared is the square root of 1 plus sinh squared theta. But notice that because of the relationship between sinh and cos, that's how we rigged this thing. That's why we chose x to be sinh theta. Notice that the square root of 1 plus sin squared theta is just cos theta. And therefore, when we now substitute for dx over the square root of 1 plus x squared, we get what? For dx, we have cos theta d theta. For the square root of 1 plus x squared, we have cos theta. Cos theta d theta over cos theta is just d theta. And now we see the answer is quite simply theta plus c. But what was theta? Since theta was x, theta was inverse hyperbolic sine x. And you see, this is the technique whereby starting with the integral dx over the square root of 1 plus x squared, we can show that we must have started with inverse sinh. At any rate, this will be reinforced in homework problems. It will be reinforced in the next block when we talk about techniques of integration. But I just wanted to again show